Okay, so section 6.6 is solving trig equations. So we're going to be looking at using different techniques in order to solve a given trig equation. So the simplest, and when possible you want to use this method, is solving by inspection. You guys have experience with solving graphically when we were studying the sinusoidal word problems. Remember, that's where you create a system of equations by taking the left-hand side of the equation and setting it equal to y, and then you take the right-hand side of the equation and set it equal to y, and graph those two equations and find their points of intersection. And also now we're going to be looking at using some algebraic techniques, using the inverse trig functions, and as well as some of those fundamental trig identities that you guys should know now. So the first method that we're going to look at is the most basic method of solving a trig equation. You will not be able to solve every trig equation by inspection, but whenever you have like sine or cosine or tangent or cosecant, cotangent equal to a ratio that's from the unit circle, it will often be the most efficient to just solve by inspection. What I mean by that is just by looking at the equation or inspecting the equation to determine the solution set. So 3x equals to 27 is not a trig equation, but it's a very basic equation. So an example of solving by inspection would be just looking at this equation and thinking to yourself, 3 times what equals to 27? You go, oh, well, if x were equal to 9, 3 times 9 equals to 27. So when you're solving by inspection, you're not thinking about applying any properties of equality, like you're not thinking about dividing each side of the equation by 3. You're looking at the equation and thinking, well, what would make this a true statement? So I have a couple basic trig equations here. So sine of x equals to 1/2, and then cosine of x equals to negative 1/2. So let's focus in on the sine of x equals to 1/2, and we're going to be solving over the interval from 0 to 2 pi. So this equation over that interval, finding the solutions, is easy because you can just think about your unit circle. Sine is positive in quadrant 1 and quadrant 2. So you know that you're going to have an angle from quadrant 1 that will make this a true statement, and an angle from quadrant 2. The angle from quadrant 1 that would make this a true statement would be pi over 6, and the angle from quadrant 2 would be 5 pi over 6. So it's just looking at this equation and thinking what values on that interval would make this true. For cosine of x equals to negative 1/2, cosine is negative in quadrant 2 and quadrant 3. So I'm thinking, okay, well, what angle from quadrant 2 would make this a true statement? And that would be 2 pi over 3. And then what angle from quadrant 3 would make this a true statement? And that would be 4 pi over 3. Okay. Now, in order to solve this graphically, or finding the points of intersection, I guess I could always make a table and plot all the points and reference my unit circle still, and then wherever I have the point of intersection. So the system that I would create here would be y equals to sine of x, and then y equals to positive 1/2. I already have y equals to sine of x graphed over the interval from 0 to 2 pi. So then if I graph the horizontal line at y equals to 1/2, we can see on that interval that there are 2 points of intersection. And if I had plotted some additional points, then I would be able to see that this point right here would be pi over 6, 1/2, and this point over here would be 5 pi over 6, 1/2. If you were to use your calculator, so graphing both of these equations and then finding the points of intersection, your calculator would only give you a decimal approximation, which sometimes that's okay, that's enough. But by solving by inspection, since this is a basic trig equation, we're able to find the exact values of this equation. And we're going to talk more about how to find the exact values of any trig equation using the inverse trig functions, but we'll talk about that in a minute. Okay, and then for cosine of x equals to negative 1/2, if you were to create a system, so y equals to cosine of x and y equals to negative 1/2, graphing, I already have cosine graphed here, so then graphing the horizontal line at y equals to negative 1/2. Again, I would have to have had more points graphed, but we know that that first point of intersection is the point 2 pi over 3, comma negative 1/2, and then this point would be 4 pi over 3, comma negative 1/2. So you could also use your graphing calculator, get the approximation for those points of intersection. So those would be the approximate solutions to this equation. Okay, now what if we want the general solution set? So the solution set over all real numbers. Then it's going to be helpful to use the inverse trig functions. Now that's not the only way to come up with the general solution set for some equations. There are some equations, like the equations from above, where if you were solving the equation sine of x equals to 1/2 over all real numbers, you could technically come up with that solution set by inspection. However, instead of determining or needing to really think about it or to remember when you can use one method versus another, just know that this method will be foolproof for any trig equation. You will be able to come up with the general solution set for any trig equation using the method that I'm about to go over. And you just have to basically memorize what these general solution sets are for inverse sine, inverse cosine, and inverse tangent. The reason I'm only using inverse sine, inverse cosine, and inverse tangent and not inverse cosecant, inverse secant, and inverse cotangent is because we could use identities to rewrite any trig equation in order to just be able to use inverse sine or inverse cosine or inverse tangent. Okay, so if you get your equation to be sine of x, or it could be a more complicated argument, and we'll go through some examples that are that. But let's say you get to sine of something equals to a number. You can come up with the general solution set by doing x equals to inverse sine plus 2 pi n, or x equals to pi minus inverse sine plus 2 pi n, where n is an integer. And I left it blank in here because those just represent you're taking the inverse sine of a ratio, as long as that ratio is between -1 and 1, so in the domain of inverse sine. If the ratio were outside of the domain of inverse sine, like it were a value that was larger than 1 or smaller than -1, then there wouldn't actually be a solution to that equation, because sine, remember, oscillates between -1 and 1. Okay, so let's say that inverse sine, let's say that inverse sine represents an angle from quadrant 1. That would mean that you're taking the inverse sine of a positive ratio. Okay, so if inverse sine is an angle from quadrant 1, so this part here represents an angle from quadrant 1. Drawing that picture. Okay. Then this angle right here would be the inverse sine of that positive ratio. And then pi minus inverse sine. Should I use a different color? No. Pi minus inverse sine would be that angle reflected over the y-axis. So that angle would be pi minus inverse sine of a positive ratio. Okay, sine's positive in quadrant 1 and quadrant 2. Okay, so the angle that would make like sine of x equal to a positive ratio true would be inverse sine of whatever that positive ratio is, as well as pi minus the inverse sine of that positive ratio. And then the plus 2 pi n, okay, that takes into account all of the coterminal angles to the angle from quadrant 1, as well as all of the coterminal angles from the angle from quadrant 2. Now let's say that inverse sine represented an angle from quadrant 4. So that would mean it was inverse sine of a negative ratio. Okay, so that would actually be a negative angle. So drawing that. Okay, so an angle in quadrant 4, inverse sine is the angle in quadrant 4. Okay, it would be a negative angle, so rotating in the clockwise direction. So this would be inverse sine, and that's of a negative ratio. And then pi minus the inverse sine. Pi minus the inverse sine would actually be that angle right there in quadrant 3. Because it would be pi minus a negative angle, because inverse sine of a negative ratio represents a negative angle that terminates in quadrant 4. So pi minus that negative angle would actually be this positive angle that terminates in quadrant 3. And then the plus 2 pi n's, where n is an integer, represent all of the coterminal angles to those angles. Okay, so that's why x equals to inverse sine plus 2 pi n, or x equals to pi minus inverse sine plus 2 pi n, where n is an integer, represents the general solution set, so all of the possible solutions to a trig equation that has sine in it. Now let's say that you have to use inverse cosine. So you have cosine of something, so like cosine of x equals to a ratio that's between -1 and 1, then your general solution set would be x equals to inverse cosine of that ratio plus 2 pi n, or x equals to the negative inverse cosine of that ratio plus 2 pi n, where n is where n is an integer. If inverse cosine is an angle from quadrant 1, meaning that this ratio is positive. So it's inverse cosine of a positive ratio gives you an angle from quadrant 1. So here is an angle in quadrant 1. I'll call that angle inverse cosine. Okay. Then negative inverse cosine of that positive ratio would just be the negative. So that angle reflected over the x-axis, that would be the angle negative inverse cosine of the positive ratio. And if inverse cosine is of a negative ratio, meaning that that angle, inverse cosine, would be an angle from quadrant 2, because you're thinking about the range of inverse cosine, remember, is between 0 and pi. So if inverse cosine is of a negative ratio, that represents an angle from quadrant 2. Cosine is negative in quadrant 2. So that would be this angle. And then negative inverse cosine be that angle reflected over the x-axis. Okay, and the plus 2 pi n represents all the coterminal angles to the angle in quadrant 2 as well as the angle in quadrant 3. Okay. Now, inverse tan, when you have to use inverse tan, that one's easy. That's only one part. So remember, the fundamental period for tangent is pi. So if you have tangent of x equals to a number, the general solution set would be x equals to inverse tan plus pi times n, where n is an integer. Okay. So if inverse tan is an angle from quadrant 1, that means it's inverse tan of a positive ratio. Remember, anytime you're taking the inverse sine, inverse cosine, inverse tangent of a positive ratio, it represents an angle from quadrant 1. Okay. Now, if we were to add pi or subtract pi, that would put us into quadrant 3, right? So if we were to either add pi or subtract pi, so if we add pi, we would end up there. That would be pi plus inverse tan. Or if we were to subtract pi, then that would put us here. Okay. Sorry, here. If we were to subtract pi. So we don't need to have two separate equations to represent all, and if we keep subtracting pi, then we would hit back in quadrant 1 and then back in quadrant 3, quadrant 1, quadrant 3, and so by putting plus pi times n, we cover all of the angles from quadrant 1 as well as quadrant 3, so where tangent is positive. Now let's say we were taking the inverse tan of a negative ratio. That would mean that inverse tan would terminate in quadrant 4, and it would be a negative angle. Remember, the range of inverse tangent is from negative pi over 2 to pi over 2, where the endpoints are not included on that interval. So that would be inverse tan, the angle inverse tan. And then if we were to add pi, that would be this angle, or if we were to subtract pi, if we were to, pi minus, the negative angle minus pi, would be this angle. And then the negative angle plus pi, would be this angle. Sorry, that took me a second to think about. So that would give you, so if you're taking the inverse tan of a negative ratio, the plus pi n would include all of the solutions from quadrant 4 as well as quadrant 2. Okay. So we're going to actually look at using this in order to come up with our general solution set. Now, the cool thing is this can be your method for solving any trig equation. Like you don't even have to think about, well, do I want to use inspection here? You can just use this method in order to come up with the general solution set, but then, which you will often need. But then if you needed to solve, like say over a interval, you could just use the general solution set in order to help you with coming up with all of the values that are over an interval. So like, let's look at this next example. Okay. So sine of 2x equals to 0. So I'm going to be using inverse sine because I have sine of something equals to a number. So that tells me I'm going to be using the inverse sine. The argument is not just x, it's 2x. So I'm going to actually have 2x equals to the inverse sine of 0 plus 2 pi n, okay? Or 2x equals to pi minus inverse sine of 0 plus 2 pi n, where n is an integer. Okay. And then now we're solving for x. So now we can divide each side of the equation by 2. So we would have x equals to inverse sine of 0 divided by 2 plus, when I divide 2 pi n by 2, that's just pi times n. And then same thing with the other equation. So we'd have x equals to pi over 2 minus inverse sine of 0 over 2, and then plus pi times n, and still where n is an integer. I'm not going to write that for each step. I'll just write that for the final. Now, inverse sine of 0, we know what that is, right? Since 0 is a ratio that's from the unit circle, we can simplify this further. But technically, this would represent the general solution set. It's just, since we're taking the inverse sine of a ratio that we know from the unit circle, we can simplify our answer slightly more, so that it's more helpful to us when we are actually finding the solutions over these different intervals. Okay, so inverse sine of 0 is actually equal to 0. Okay, so that would mean that this would become x equals to just pi times n. Okay, or x equals to pi over 2, and it would be pi over 2 minus 0 plus pi times n. So it'll just be x equals to pi over 2 plus pi times n, where n is an integer. Okay, so this is the general solution set to our equation. Sine of 2x equals to 0. We can use that general solution set to help us determine what the solutions are over the interval from 0 to 2 pi. So I can go to this first equation and go, okay, so if n were equal to 0, that would be x equals to 0. Well, that's on this interval. And then if n were equal to 1, x would be equal to pi. Well, pi is on this interval. Okay. If n were equal to 2, x would be equal to 2 pi. 2 pi is not included in the interval. So now I'll go over to this equation. I go, okay, well, if n were equal to 0, x would be equal to pi over 2. If n were equal to 1, pi over 2 plus pi is 3 pi over 2. 3 pi over 2 is on that interval. Okay. And if n were equal to 2, that would be pi over 2 plus 2 pi. Well, I can see that that's going to be a value that is outside the interval from 0 to 2 pi. So these are actually the solutions to that equation on the interval from 0 to 2 pi. And we can go through a similar process for coming up with our solution set over the interval from negative 2 pi to 0. So instead, because we're going to have negative angles as part of the solution set, well, if n was equal to 0, 0 is on this interval. So I'll have x equals to 0. If n is equal to negative 1, we'll have negative pi. And if n were equal to negative 2, that would be negative 2 pi, and negative 2 pi is not included on the interval. So I go over to the other equation. Okay, so when n was equal to 0, x equals to pi over 2. Pi over 2 is not on the interval from negative 2 pi to 0. So I'll go down to negative 1, or let n equal to negative 1. So pi over 2 minus pi. So when n is equal to negative 1, that will be pi over 2 minus pi would be pi over 2 minus 2, negative pi over 2. Oh, where'd it go? Okay. And if n were equal to negative 2, that would be pi over 2 minus 2 pi. Well, that's pi over 2 minus 4 pi over 2, which would be negative 3 pi over 2. Well, negative 3 pi over 2 is on the interval that we are trying to find all the solutions on. So negative 3 pi over 2. And if I made n equal to negative 3 pi, that would be pi over 2. So if I made n equal to negative 3, that would be pi over 2 minus 3 pi. Okay, that would be pi over 2 minus 6 pi over 2, which would be negative 5 pi over 2. And that would be outside of the interval. Okay, so these would be my solutions over the interval, to that equation over the interval from negative 2 pi to 0. Okay. So next, let's solve the equation tangent of 2x equals to 1 over the following intervals. So over the interval from negative infinity to infinity, so basically over all real numbers, this is the general solution set. Okay, so we'll have 2x equals to inverse tan of 1 plus pi times n, where n is an integer. Okay, and then we can divide by 2. That's where n is an integer. Since 1 is a value for tangent on the unit circle, I can simplify that. Inverse tan of 1 is pi over 4, the angle pi over 4. So pi over 4 divided by 2 is pi over 8. Okay, so pi over 8, x equals to pi over 8 plus pi over 2 times n, where n is an element of the integers. So that is our general solution set to the equation tan of 2x equals to 1. Then if we want to use that general solution set, we can come up with all of the solutions over the interval from negative 2 pi to 2 pi. Okay, so I'm going to start, I think I'm going to actually first find, what do I want to do? So I'm just assigning values to n. So I'm going to actually just start when n is equal to 0. We would have pi over 8. Okay. And if n were equal to 1, pi over 8 plus pi over 2 would be pi over 8 plus 4 pi over 8, which would be 5 pi over 8. Okay. That's between negative 2 pi and 2 pi. Okay, so that was when n equals to 1. When n equals to 2, that's pi over 8 plus pi, which is pi over 8 plus 8 pi over 8, or 9 pi over 8. Okay, that's still between negative 2 pi and 2 pi, because 16 pi over 8 would be 2 pi. Okay. Now, if n were equal to 3, okay, that would be pi over 8 plus 3 pi over 2. To get a common denominator, that would be equal to pi over 8 plus 12 pi over 8, so 13 pi over 8, which is still on that interval. Okay. If n were equal to 4, that would be pi over 8 plus 2 pi. So that's obviously going to be outside this interval. Okay, so now I want to look at using negative values for n. So if n were equal to negative 1, that would be pi over 8 minus pi over 2, or minus 4 pi over 8, which would be negative 3 pi over 8. Okay. If n were equal to negative 2, that would be minus pi, or minus 8 pi over 8, which would be negative 7 pi over 8. If n were equal to negative 3, that would be pi over 8 minus 3 pi over 2, which would be pi over 8 minus 12 pi over 8, or negative 11 pi over 8. Lots of solutions to this equation over this interval. Okay. And if n were equal to negative 4, that would be minus 2 pi. Well, that's okay, because pi over 8 minus 2 pi is going to give us an angle that's in this range. So that would be pi over 8 minus 16 pi over 8. Okay, so we get minus 15 pi over 8. And then if we subtracted any more, so like if we made n equal to negative 5, that would go outside the interval. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 solutions on the interval from negative 2 pi to 2 pi. So I think that trying to solve something like this by inspection would be a challenge, and it's nice, and especially over an interval this large, it's nice to be able to use the general solution set in order to help you come up with all of the solutions over a particular interval. So I'm going to stop right here, and I'm going to break this lesson up into multiple videos because there's a lot of examples here. I wanted to provide you guys with a lot of examples. So I'm going to make another video